Okay, so again, now things about motion, forces are involved, no, in making these objects move, no, in so many ways, no. But we have a separate topic probably, no, for the inclusion of a force, no, in motion, no, and that will be on the Newton's laws of motion, no, specifically Newton's second law, no. But right now we are not yet there, so we will just talk about now what we call the idea of kinematics, no. So motion, no. So there are two main branches of mechanics, no. So these are the two. So kinematics is again a field where we talk about motion, but we do not mention, no, the involvement of a force, no. To simplify the idea of speed, distance, no, and maybe the idea of acceleration, no, without thinking about, no, an even bigger knowledge of force, no, then we simplify it, no, by calling it kinematics, no. Dynamics includes the study, no, of factors like forces and physical properties of bodies, no, which affect motion, no? So but right now we are not yet there, no? So we will simplify it by removing the knowledge on why objects move, no, which is of course the effect of a force, no. So we will just simplify our motion, no, knowledge on motion, no? Okay, so motion, what is motion, no? When can we say that a body is undergoing motion, no? So we will always think of motion as involving, no, a certain reference point, no? So if there are two locations here, no, like point A, so we will always ascribe it now with some reference point, no? Just like when we talk about displacement, no? How do we know that a body, no, underwent a certain displacement? So we will have a reference or a starting point, no? Now after some moment or some unit of time, no, we will see that a body will now change its location, no, from A to B, no? And that is what we call a motion, no? So our reference or our starting point may be A, and then after a while, no, we see the body to be already in letter B, no? So motion, no? So rectilinear motion is when bodies will simply move, no, in a straight line like this, no? Now when we go around some subdivisions, no, our subdivision roads are commonly, no, straight lines, no. Houses are arranged, no, in blocks, no. So we may see there several houses, no, but we see some portions of that subdivision to be having, no, some straight roads, no. And then after that, no, you will make a turn, no, because the block ends, and then there's now an intersection, no? So but that's one kind of a motion, no, straight line motion, no, if you walk in blocks of roads, no. Another type is when you make a turn, no, in a rotonda, no. So if you are familiar with the CPU flagpole, no, and I do hope, no, that at one time you went, no, you were able to visit the university. In the flagpole area, that's a rotonda. So the cars there do not travel in a straight line anymore, no? So maybe that could not be considered anymore as rectilinear motion, no, if you make a turn in that rotonda, no? So motions of bodies that is done in a straight line, no, is called as rectilinear motion, no? Now, maybe another way of picturing out rectilinear motion is when something is falling down, no? So when you have an object, no, that you're holding and you suddenly slip, it slipped from your hand, no? Then it's most likely direction is to go down, no? I have not seen an object that slipped my hand that went up, no? So falling is somehow, no, can be attributed also as a rectilinear motion, no? It travels in a straight line, no? Now, if you consider the distance here, so if there's a distance, no, maybe distance S, usually we label it as S, no? And then there's a unit of time, no? maybe no, we label time as t. No? So if you divide the distance or displacement by time, then you get speed. No? So speed is your change of this distance, no, per unit time. No? Now, if the speed is also increasing or changing, then that's what we mean by acceleration. No? So acceleration is when the speed this time is no longer the same, no? But you keep on increasing and increasing your speed. No? Like if you are seated in a sports car or in a car, no, that is trying to no catch up with another vehicle, no, that is ahead of him, no. So most likely that car is accelerating, no, because he has to no overtake no, another vehicle, no. Okay, but also no acceleration may happen when you are trying to suddenly no step on the brake and you are now trying to slow down. No? That is also a change in speed. No, when you suddenly no step on the brake of a car, and of course no you'll feel something no in your body when that happens. No, so again no the change in the speed. No, we call it as acceleration. So acceleration can happen whether you are speeding up or you are trying to slow down. No? Okay, so motion no, denotes the change of position of a body no, with respect to some reference point. No? So maybe there's a what no a street light there no, where this boy is probably no leaning or he's staying there for a while. No? And from that reference point, some car no, moves away from him. So maybe the car is already at a certain distance not from him. No? So again, no, from this location, no, maybe no, the car travels, no, or is in motion compared to the boy. No? Okay, now I think you are right now seated in your you are seated in your chair there. No? Can you consider yourself to be in motion, guys? The standpoint of this boy, the car is moving because it is moving away from him. No? But actually, no, if we'll try to imagine ourselves, no, while we are seated right now, no, in our chair, or maybe you are lying in your bed, no, uh, early morning, no, we are all actually in motion. No? If we think of, and we are in the Earth, no, and the Earth is constantly rotating on its axis, no. And this, even though the Earth, no, or while the Earth is rotating, no, on its axis, it is also going around the sun, no, and we call it as a revolution. No? So if there's something, or if there's somebody, you know, outside of the Earth that is observing us, no, like an astronaut, no, happens to see the roof of our house, no, we will notice that that astronaut will say that that house, no, is moving, no, relative to the Earth because the Earth is rotating. No? So generally, no, none of us is actually no at rest. No? We can also think of motion, guys, as something relative. No? Now imagine yourself to be flying in a plane. No? So let's say you are able to have a vacation. No? You are able to have a vacation and you took a flight no, in an airplane. With you, no, is your parent, no, or both your parents, no. There are three of you, no, in the plane. No? Now, relative to each other, no, let's say you are seated in the plane, your mom, your dad, you, no, are seated in the plane. You will see now that your mom and dad are not in motion, no. Relative to you, no, your dad and mom, no, since you are all inside the plane, you are not moving, no? You are not in motion, no. But relative to the people that are in the airport, no, who give you a ride, no, para makalabot ka mo sa airport, you are already very far away na pinakalupad ng eroplano. No? Okay, so again, now something about motion that is kind of relative is when we speak of certain reference point. No? So maybe inside, no, people who are inside the plane relative to each other, you may not think of yourselves to be in motion with each other. No? So somehow, now that's the idea where we can say that motion is relative. No? So again, now we have here a speed. No? So we can think of that as the speed. No? So 60 kilometers per hour. Now, how do we understand that? No? Now, if we convert that with some distance and time, no? Supposing a car now was able to cover 120 kilometers in 2 hours, no? Then we can say that the average speed, no, of the car, which is total distance over total time. No? So we say that again, no? Average speed or average velocity, no, can be equated, no, as total distance over total time. No? So if you divide that, now that's 120 over 2, no? Or that's 120 kilometers over 2 hours. So that gives you now an average value of 60 kilometers per hour. No? And an average velocity again, which we can write now with some symbols V bar. No? Just like mean, no? We use a bar at the top of X. No? So that one tells you of an average value. Now, this value 60 kilometers per hour does not mean that for 2 hours, the car was actually moving only at 60. No? We could not do that for 2 hours. No? So highly unlikely, or it's quite impossible to do that. No? So what we can think of now is that basing on the total distance and the total time, no? Roughly that's how fast the car is moving. No? But again, no, we could never say that all throughout the journey, no, that is happening. No? So again, no, that's the idea of an average velocity. Okay, now from Iloilo City to Rojas City, no, does the bus travel, no, 60 kilometers per hour? Probably yes, no. Now, if initially, no, the car travels at 70 and then for some reason it changes its velocity, no, to 50. So the first velocity, we can call it as VI, no, initial velocity or initial speed. V sub F is also final velocity, no, or velocity number 2. No? If that's 50, no, so you'll notice that if you'll add up 70 and 50 together and divide it by 2 values, you can also get an average. No? So an average speed, aside from total distance over total time, can also be, no, determined by getting, no, what we call a final value. No? So we can call it as V sub F. And then we can subtract it with V sub I. No? Oh, no, sorry. No? It should be V sub F plus V sub I mean. No? Final velocity plus initial velocity. No? And if you divide that by 2, no? And that's how we get the average usually, we can still get, no, the same result of 60 kilometers per hour. No? 70 plus 50 is 120. No? 120, if you divide that by 2 values, no? Then that is also another way of getting the average value. No? So here are 2 ways of getting our average velocity. So that's another way of getting average value. So that's initial plus final, or final plus initial divided by 2. No? So 70 plus 50 is 120, no? Divide by 2. No? 2 is our value, no? Because we have 2 values of velocity to consider. No? So that's just getting an average value. No? Okay, now so far we have, again, no, this average values. No? So 2 average values that we can use. No? Now, if you're going to simplify the one above, no? If you're going to change, no, it. So from our first equation above, we can write our value for distance to be V bar times t. No? We can also write it like that. No? So average value can be the product of time and average speed. No? That gives you your total distance as well. No? And these are helpful equations, no, in our later discussion. No? So let's look at the three different ways now which velocity may change. And number one is the magnitude alone of the velocity may change. No? So that's a change in velocity with the direction remaining the same. No? So again, maybe now for number one, we can consider a car that is traveling in a straight line, and what happens is that it is increasing and increasing its speed. No? So that's what we call a change in velocity. No? So the velocity is the one, no? V is the one that is simply increasing here, but there is no change, no, of direction. No? Its direction remains relatively, no, the same. No? So V is increasing, but not its direction. Number two, no, the direction alone may change, no, with the magnitude remaining the same. No? Now this one is occurring when a car is making a turn. No? So supposing, no, it's a circular path, we realize that you can keep your speed here the same. No? You can maintain your speed, no, but you're always changing direction. Now, when you are in a rotunda or you are making a turn, you're changing direction. So change of direction can be also considered as a changing velocity. And number three is when both are occurring. You are making a turn, and at the same time you are increasing or you are decreasing your speed. Again, for number one, an object is maintaining its speed, increasing maybe its speed, but traveling in a straight line. So that's number one. Or maybe straight line, but the body is slowing down. So three ways of okay, let's move on. So when the velocity changes, the motion is considered to be accelerated already. So we can have types of motion. We call one type to be uniformly accelerated. And when your velocity is changing, then that's what we call now as an accelerated motion. Now, there are three types of rectilinear motion. The first one that we will mention, and this is related to the changing velocity. The first type is what we call body. The body starts from the left, then it is moving to the right, but it is traveling with regular change in distance. So every 4 meters, the body covers a time of 1 second. So from left to right, ang first 4 meters was able to be covered in 1 second. The next 4 meters, the body still covers that in 1 second. The third 4 meters was covered in another 1 second. And the last 4 meters was covered again in another 1 second. How do we picture out the speed of the body? What can you say about the speed of the body? A steady value. Okay, so the velocity in each of these interval is the same. So paano natin kwaon? How do we get velocity again? That's displacement over time. So they all have the same value. Now, what's the direction of the body? The direction of the body, is it changing or not? Now, since the body is traveling in a straight line, going from left to right, its velocity or its direction is not changing. It has one same direction. So therefore, we can say that the body is traveling with a uniform motion or uniform velocity. Kaya wala naga-change ang iyang velocity. Now, we call that type of motion, guys, as uniform motion, which is the first type. The uniform motion happens when the velocity is the same, no, all throughout. No? Okay, now next is same, maybe not same illustration, no, but maybe now a different condition is occurring here. No? So here is a body that is no, moving no, relatively no, with different distances. No? But now the time interval for each of these lengths no, is occurring at the same time. No? So 1 second for each of this interval, but how will you imagine this body? No? This body is speeding up no, from the first interval to the second. It seems that it is increasing its speed. Then suddenly it changes its speed. No? Naghinay siya and then nagdasig na naman. No? So if you try to imagine that, now that's a body that is changing its velocity. No? So its velocity is changing no? From 2 na 6, meaning it increases its speed and then slows down and then again no? Increases its speed. No? Now maybe no, this is the typical object that we will be actually seeing on the road. No? We cannot actually no, imagine a vehicle that is having no, a speed that is steady all throughout. No? So in the road, no, you have to adjust your speed no, from time to time. No? So we call this type of motion. No? So if you'll try to get no, the difference of 6 minus 2. Pila ang 6 minus 2? How much the value? Values that we get no, that are now labeled in green. Sometimes they are positive. Sometimes they are negative. Again, negative when the last value minus the previous value no, is larger no, ang previous value. No? So 4 is smaller than 6. No? So you get negative 2. No? Now we call that value as acceleration. No? Acceleration is the rate of change of the velocity no, per unit time. No? And look at the unit of acceleration. It is now in meters per second square. No? So our time is being squared this time. No? So, but how did we get this? We get the difference of two velocities per unit time. No? So if you subtract the two values of velocities. No? Now, what can we say about our acceleration here? The acceleration is not constant. No? So the velocity, the blue labeled values no, are also not constant. No? From 2, it becomes 6, it becomes 4, it becomes 5. So we say that it's not constant. No? It's not equal to some constant value, including our acceleration. No? The acceleration is not also constant. No? So when this happens, we call the motion there to be accelerated motion. No? In this previous illustration, what if we will subtract 4 minus 4? What is our difference?
0.
0. No? So it means that when acceleration is 0, no? Because there is no change in the velocity, no? Then it's also classified as uniform motion. No? So here we'll see that acceleration, if acceleration is the difference of two velocities, here our acceleration becomes 0. No? What's the third type of motion? No? What's the third type? No? If there are 3 types of motions, then what's the third? No? Let's look at the third one. No? Okay, sorry. No? So we only mentioned about 2 no, for this time. No? But actually, there's a third one, which we call as uniformly accelerated motion. No? And that uniformly accelerated motion is when we keep also the acceleration to be constant. No? Now let's have some observations. So velocity is not constant. It's changing. No? When it is increasing or decreasing, then what we see is that the body is accelerating. No? So again, now this is the one that we notice with our figure 2. No? So acceleration is not constant. No? It's either no, increasing also or decreasing. So decreasing or negative acceleration means the body is slowing down. No? So positive acceleration happens when the velocity increases, and negative acceleration happens when the body is slowing down, or there's a decrease in its velocity. Now let's go to the third type of motion here. So we have here a body that is increasing its speed. So from 2, it becomes 4, then it becomes 6, it becomes 8. And supposing in every time interval again, this happens in every 1 second still. So therefore, if we'll get the velocity will be 2 meters per second, then 4 meters per second, then 6, and then 8. So we have an increasing velocity, and we notice that the increase there is kind of constant. How much is the increase? We can see that in the value of the acceleration. The same. So this is a type of motion that we describe as uniformly accelerated motion. Now, can we achieve in real life this kind of condition that a body keeps on increasing and increasing its speed? Can we do that infinitely? Can a body increases its speed infinitely? This in this topic here, so this portion of motion now, we describe it where its velocity is not constant. However, its acceleration is constant. We call this as a type of motion, guys, that is uniformly accelerated motion. And again, one type of this motion is when an object falls at some point. So as it falls down, it may probably achieve this condition, but after a while, it will not already keep on increasing its speed. And we will explain that now when we go to that free-falling body discussion. Okay, now allow me to write an equation of our acceleration. So again, how did we get our acceleration value? Again, if this is our final velocity, so this is our final value. So 4 meters per second is final, VF. Initial is V sub I, that's 2. So the difference of the 2 is now 2 meters per second. And how long is this interval? Again, that's also 1 second. That's 1 second. So if the whole interval is 2 minus the previous interval, which is 1 second, so the time t is also 1 second in every value. So Vf minus Vi over t gives you your acceleration value A. Any question?
None.
If we transform our equation, this equation on acceleration, if we cross multiply together A and T together, if you multiply these two, so this is what we will see. And if we transpose this negative V sub I to the other side, go joining A times T, then we will eventually have this expression. So this expression is a result of our previous equation that we wrote earlier. Now, the second equation is a combination of our S equals V bar times T. And just like this one as well, it's also taken from our V bar times T value. So let's say again, we are given A equals Vf minus Vi over T. Now cross multiplying these two, cross multiplying, that will give us now 80. And that leaves us with Vf minus Vi on the right side. Now if we will try to transfer v sub I on the left. So v sub I, if we join it with AT, will leave us now with VF on the right side. No? Now, our equation or our equality of equation, we can actually swap together VF to be equals to VI plus AT by the principle called symmetry of equations. So if A equals B, then B is equals to A. We can actually exchange that. And therefore, now we end up with our first equation here. Now our second equation, you can probably think of our second equation in this way.
Yes, sir.
So we have S equals V bar T, then V bar is also VF plus V sub I over 2. Now we will be substituting the V bar value to the left equation. We will try to substitute it. So again, if we will try to substitute V bar with VF plus V sub I over 2, we need to multiply the whole thing with letter T. So that's what we have for our S. So we replace our V bar value. Now, we will try to distribute our T to the expression inside the parentheses. So again, distributing, then we split the denominator 2 to each value, but what we did was we multiply T to each of the expression inside. We multiply T. Then that's what we get. Now we are going to substitute our expression V sub F, which we already know from here. If you'll try to recall this one, our V sub F can actually be equivalent to VI plus AT. And that's what we will substitute next to our expression. So again, now we replace V sub F with our expression earlier. So V sub F being VI plus AT. Then we will try to multiply this expression T to each value inside the parentheses. And split our denominator 2. So let's move on to this side. So we could have a bigger space. Let's move on here. Or this is what it looks like now when we finally distribute T to the expressions inside. Now, which values are now the same? What values can we now combine? If you think of that as an algebraic expression, which algebraic expressions can be combined together? Okay, so you'll notice the ones in those with check marks are actually the same expression. So if there are x, now what is x plus x or 1/2 x plus 1/2 x in algebra? So again, the resulting equation is now similar to our expression here, and we are simply deriving this just to show that they all come, they come from this expression. Now the third expression could also be taken by using this expression that we put in a box. However, for you to get that, there are two values that you have to know aside from V bar being VF plus VI over 2. We can also express our T here if we will write the value of T to be equals to VF minus VI all over 8. If we will use this expression for T, then you can multiply V bar times T. If you multiply V sub V bar and T together, you will also get S. And in that way, this is how we will get a squared expression now for number 3 equation. So for this third equation here, we can get it by multiplying V bar with T and getting the value of S. So here are things that we can probably consider also when we deal with motion. So these are important terms. If velocity increases, we have a positive acceleration. If velocity decreases, then we have a negative acceleration. When it says that a body starts from rest, what is being indicated there? that the initial velocity is the one, no, that is being labeled as given, no, then the initial velocity is 0, no, when it mentions that the body starts from rest. Now, this is an important statement. No? It is actually a given. No? Now, in the equation that we just saw, no, you must have at least there 3 known values. No? And if this is already a known value, ang word nga starts from rest, no, then you will only look for 2 more unknowns. No? So again, in order for you to solve an expression, you must have 3, no, something like 3, no, 3 known values. No? And usually this one is an implied given. No? It does not say that it is an initial velocity, but the statement is telling you that that is a given value. No? Now, another word, maybe the body suddenly stops. No? That is also another given. No? And this time, what is being implied or being made as a given is the final velocity this time. No? So the body stops suddenly, no? Or it comes to a halt, no? Then therefore VF must be 0. No? So these are again given implied values. So they are not stated as a specific value numerically, no? But it's a statement that is implied to be given. No? So I want you to note them down. So a jeep starting from rest, no, accelerates at a rate of 4 meters per second square. No? So what is given is the word from rest, no, which is an implied given, guys. That must be V sub I, no, which is 0. No? That's one given. The acceleration is another given value. So if we say that we need 3 more given values, then this one is not yet complete. No? With this, we cannot yet solve the problem. No? But if we look at letter A, no? Question letter A. So what is the velocity of the body after a time of 6 seconds? No? So now, if we look at the first question, we now complete the 3 required given values. No? So therefore, we are able to solve letter A. We are looking for the final velocity. Now, since we have 3 known values there, we are able to solve it. No? But what about letter B? No? What distance does it travel after 6 seconds? No? So we are looking for S. No? S is usually referred to as distance. So we have 3 known values because if time there is given to be 6 seconds, no, then we have 3 known values already. So we are now able to solve letter B as well. No? Letter C, what distance does it travel during the 6 seconds? Then again, no, that could be another situation. No? Is 0, no? So we can simply cancel this. No? The initial velocity happens to be 0. No? Then all that we will be having is this side a t square over 2. No? Okay, so a is 4 positive. No? Okay, it is increasing its speed times time, no, which is 6 seconds. If we square 6 seconds, then that will be 36. No? Then divided by 2. No? So 4 divided by 2 is 2 times 36 is 72 meters, no? Because S is a distance. And then lastly, no, we will have to solve for the time, no, during the distance traveled only, no, the only on the 6 seconds. No? Now, letter B is a problem that allows us to find the distance traveled for 6 seconds. No? What we did not solve is the distance traveled for 5 seconds only. No? Now, if you'll try to find S, no, traveled for 5 seconds, then maybe, you know, the answer there is this one, no, ining 50. No? This is our distance traveled for 5 seconds. So the one that we solved here. No? Now, if you'll get the difference, no, of the distance traveled for 6 seconds, which is 72, and the distance traveled for 5 seconds, which is 50, then the distance traveled only during the 6th second. So this is the distance traveled only during the 6th second. Then the distance traveled during the 6 seconds is the difference of S6 over time minus S5, which is 22. So we are simply interested there of the distance for that particular moment in time.